This lecture is on refraction in spherical lenses. Now, the speed of light inside a medium is different from that inside of a vacuum. It's slower inside a medium than it is inside a vacuum. Now, the refractive index is defined to quantify that. So it is defined as n, the refractive index, is the speed of light over a vacuum divided by the speed of light in that particular medium. So each particular medium that light can travel through, say glass, water, will have a different refractive index. Now, if we visualize light waves entering a medium, inside the medium and outside the medium will have different refractive indices. We'll call them N1 and N2. So this line represents the surface of the medium. It could, for example, be the surface of a piece of glass. And on the other side is just air. The crests of an incoming light wave we can visualize like this. The direction of propagation of the light wave is perpendicular to the crests of the wave. Inside the medium, the crests are slowed down, so they kind of stack up on each other like this, getting a little bit closer. Note that as we stacked them closer to each other, they also changed angle somewhat, and this means the direction of propagation also changed, because the direction of propagation is at a right angle to the crests of the waves themselves. Now we'll use some geometry to find out exactly how the direction of propagation changes. And we start by rearranging the definition of the refractive index inside this first medium with refractive index n1. The speed of light c is equal to n1 v1, just rearranging this equation. Inside the medium, the speed of light c is also equal to n2 v2. Now the velocity of any wave is equal to its wavelength times its frequency. And then if we cancel out the f, we get n1 lambda 1 equals n2 lambda 2. Or lambda 2 is just n1 over n2 lambda 1. Now here's the wavelength outside of the medium, outside of the glass. And here's the wavelength inside of the glass. Let's redraw these triangles. Here they are with lambda 1 and lambda 2 labeled. We'll just call this shared side A. Note that this angle here is the angle of incidence, theta 1, and this angle here is equal to this angle, also theta 1, due to geometry. Similarly, this angle here is the angle of incidence of the outgoing ray. Whoops, I meant to call that theta 2. And then this angle here is equal to it, also theta 2. The trig gives us that sine theta 1 is lambda 1 over A, and sine theta 2 is lambda 2 over A. A little algebra using these three equations then will give us n1 sine theta 1 equals n2 sine theta 2. So this is the relationship that tells us about the trajectory of the incoming ray and how its angle of incidence is changed when it's transmitted into the material. And this change in angle is called refraction. Let's draw a picture. So here's the incoming ray with an angle of incidence of theta 1. Here's the refracted ray with an angle of incidence theta 2. The materials have refractive index n1 and n2. And the equation that we just derived relates these quantities so that if we know, say, the refractive indices and one of the angles, we can get the other angle. This is called Snell's law. So one implication of all this is that if we build a convex lens, then parallel incoming rays will be bent inward toward a focus. With a concave lens, parallel incoming rays are bent away such that their backwards extrapolation of the transmitted rays passes through a focus. Let's do a sample problem. Is the image of this object that's created by this lens magnified or shrunken? Is it right side up or inverted? Is it real or virtual? First we draw a ray that's parallel but then gets bent through the focus. Then we draw one that starts by going through the focus and then gets made parallel, and where they intersect, there's an image. We can see that this image is shrunken, it's inverted, and it's real. It's real because the rays are actual rays intersecting, not just extrapolations of rays. Now let's do some similar homework problems. For homework problem 4, consider this situation, answer the same questions, but now in this situation we have the object being a little bit closer to the focal point. For problem 5, answer the same questions for this situation, with the object inside the focal length. For homework problem 6, answer the same questions now for a concave lens and an object positioned outside the focus. Now in the last video we talked about the lens equation, and we were applying it there to spherical mirrors, but it applies to spherical lenses as well. You just have to use a somewhat different sign convention. A positive object distance means an object on the left side of the lens. At least that's how I've been drawing it here. You could always flip left and right. A positive image distance means an image on the right side of the lens, or more generally, on the opposite side of the lens from the object. Positive focal length means a convex lens. Negative focal length means a concave lens. The magnification equation applies just the same. Now the curvature of a lens and the material that it's made of are related to the focal length by something called the lensmaker's equation. Here it is. So if you need a lens of a particular focal length and you know what you're making it out of, you can determine what the shape of the lens has to be. That is the radius of curvature. So this is presented sometimes with different sign conventions. The way I've written it here, if you treat the radii as positive for a convex lens, then you'll get a positive focal length. For a concave lens, think of the radius of curvature, the radii of curvature as being negative, and then you'll get your negative focal length. I had written 1 minus n here, but it should have been n minus 1. Now it's fixed. Now one interesting consequence of Snell's law is if you have a ray that is exiting a medium with a higher refractive index, then as theta 2 gets bigger and bigger, because n2 is bigger than n1, eventually sine of theta 1 is going to become greater than 1. And that's not allowed because sine of a real number is between minus 1 and 1. So if Snell's law says that sine of theta 1 is greater than 1, then something's up. What's happening is that the refractive outgoing ray, eventually its angle of incidence becomes 90 degrees, and at that point it can't increase anymore because it's just parallel to the surface of the material that it's exiting. When this happens, there can be no more refracted ray, and the ray is entirely reflected, and it stays inside the material. This phenomenon is called total internal reflection. And the angle at which this begins to happen is called the critical angle, or theta c. And from Snell's law you can show that the sine of the critical angle is equal to n1 over n2. So an underwater diver looking up at the sky can see the sky if they look directly above themselves, but if they look over at an angle more than theta critical from the horizontal, or from the vertical I mean, then there's total internal reflection and they don't see the sky, instead they just see a reflection of the seafloor. Now we'll briefly discuss the phenomenon of polarization. Light is a transverse wave. That means its oscillations are in a direction perpendicular to its direction of travel. So light traveling horizontally may be vertically polarized, like this. If this light wave is traveling toward us, then the direction of the displacement of the wave is vertical. But you could also have horizontal polarization or anything in between. Now polarized sunglasses work by having a polarized filter that blocks out specifically the horizontally polarized light, because reflected light reflected off the, say, the ground or the surface of water tends to be horizontally polarized. Now the angle of incidence at which that polarization is maximized is the angle at which the reflected and the refracted rays are at right angles to each other. Now it can be shown with geometry and Snell's law that the tangent of the Brewster angle is equal to the refractive index of the higher refractive index medium divided by the lower refractive index. And that's your last homework problem, to show that the tangent of the Brewster angle is equal to n2 over n1.